let us go over to the whole eigenvalue distribution. And in assignments, you already looked on eigenvalues of Wishart matrices, and you saw that there is in our regime a quite meaningful limit. But we should try to understand, first of all, that we also have concentration on this limit, and in particular, can we really calculate this limit? I mean, I gave you the formula in the assignments, but can we also derive this formula? That's what I want to do maybe today and probably also next time. Yeah, so maybe let me recall our setting again. Okay, we are looking on independent draws, independent copies of our p-dimensional vectors, which have a Gaussian distribution. And now I want to specify to the simplest case where the covariance of this Gaussian distribution is the identity matrix, which just means that all components of my vector are independent, and each of them has the standard Gaussian distribution. So they are independent, and each xk has a distribution 0. And in general, we can have here a covariance matrix, but now in the following, I will specify to the case where this is the identity matrix, the simplest case. So this means I have all the entries which I have here are independent, and they are Gauss distributed. Good. Then we look on X. This is this matrix where I'm putting in all my data, x1, x2 up to xn. So this is a p times n matrix. And we look on the corresponding, essentially the square or x times x transpose. So we look on what I call sigma hat. So this is 1 over n x transpose, which is written in terms of the vectors is 1 over n, the sum k from 1 to n xk transpose. So this is a p times p matrix, independent of n. Okay. Yeah. And maybe I have here this 1 over n, which is also a good normalization. As we will see later, this actually guarantees that if we go to a limit, that this really converges to something. I mean, if I take here 1 over n, this means I'm rescaling the entries of my x's by 1 over square root of n, which means that I'm changing. I could also say I take now the matrix 1 over square root of x, which means the entries of this are still independent, but each of them has a Gauss distribution where the variance is 1 over n, not 1 anymore. And of course, this guarantees that things don't explode if n goes to infinity in a meaningful limit. So this is a good normalization, having the 1 over n here. Good, but now the question is, what can we say about the eigenvalues? Okay, so this is X itself, X is a rectangular matrix, so this doesn't have eigenvalues, this has singular values, but singular values are essentially the eigenvalues of this guy. So the sigma hat is a square matrix, p times p, and of course it's also self-adjoint, or it's symmetric, which means it has real eigenvalues. Okay, so let me denote them. So it has p eigenvalues counted with multiplicity. And I call them lambda 1 up to lambda p. Yeah, okay, and maybe, let me do this more general. If I have a matrix, if I have a symmetric matrix, I call the eigenvalues, I denote them by lambda 1 of A, and I order them. So lambda 1 is the smallest, then the next one is lambda 2, and so on, up to, and the last one, the largest one, is lambda p. So this should be the eigenvalues counted with multiplicity of a matrix, and we consider here symmetric matrices, so that we really know we have p eigenvalues, and we also know they are real. Okay, so of a symmetric matrix, A is symmetric, so A is the same as its transpose, and it's a P by P matrix. Yeah. Okay, and of course again our question is, for our Gaussian random matrix, do we have concentration? And we know we have concentration for Gaussian inputs if we have Lipschitz functions. So it's a question again, are the eigenvalues Lipschitz functions? For the largest eigenvalue, we saw this, and for any eigenvalue, this is also the case. So that's an important point. I mean, really, eigenvalues are complicated nonlinear functions without really having concrete access to them by a formula, but at least they are really Lipschitz functions, so they are not too bad. So they are not varying too much. So then one knows, so one has, as for the maximal eigenvalue, that if I, what means Lipschitz functions? I should take two matrices, and I should compare the difference of the eigenvalues by the difference in the corresponding norm. Okay, and so I should compare the ith eigenvalue of A with the ith eigenvalue of B for two matrices, and I should compare this with the corresponding norm, and the norm, I mean, which I'm using, I mean, if I'm looking on my function as a Lipschitz function, I'm going from R to some high dimension. I'm looking on my object as a vector. Here I arrange my xij into a matrix, but for the point of view whether it's a Lipschitz function or not, I consider this as a function from R to some high dimension, and here it is p times n to R. And the norm which I consider for a vector is the Euclidean norm, which for a matrix is called Frobenius norm. Okay, so this means, but in particular, I mean, I can estimate, first of all, this difference against the operator norm, which is really the thing for matrices. So one has that this can be estimated against the operator norm of A minus B. And I mean, this is some property which maybe, okay, it's not totally obvious, but there's some while inequalities or while formulas which tells us something like this. So we take this as given, and we know that we can estimate the operator norm against the Euclidean norm, which is the Frobenius norm, A minus BF. So the Frobenius norm, or the Schur norm, or the Hilbert-Schmidt norm of a matrix is just the square root of the sum of the squares of all entries, which just means I'm looking on my matrix as a vector and calculate the usual Euclidean L2 norm of this vector. Okay, and I mean this is really considering my, let's say, an n times n, or n times n. No, I have here p times p matrix as a vector in p squared. Okay, but usually this is here is quite bad. I mean, I'm losing here quite a lot. I mean, looking on my guy as a matrix is really the good thing, and there this here is much better. But okay, but from the Lipschitz point of view, it's really, I have a mapping from the R to the p squared to R, and this here tells me that this is a Lipschitz mapping. So this means the map A, which is the map which maps A to the ith eigenvalue of A for each eigenvalue, for each lambda I, for the lambda ith eigenvalue is Lipschitz. And then of course I'm usually not interested in just one particular eigenvalue. I mean, if I'm interested in one, then probably it will be the largest one. This is special. But I'm usually not interested in the 17th eigenvalue, but I'm interested in all of them together. So I want to know all of them. So I consider the mapping where I map A to the collection of all eigenvalues. But this is just putting together Lipschitz functions. Each of them goes to R. And then together they go to R to the P, and this is then still again Lipschitz. That's also something which we addressed when we talked about Lipschitz function. So also the mapping which maps a matrix to the collection of all its eigenvalues is a Lipschitz function. And I mean, the collection of all the eigenvalues is usually what we draw in our numerical simulations as the histogram, looking where the eigenvalues are. Okay, so for each eigenvalue, this is Lipschitz, but then maybe more to the point, what we really want is the map where I'm going from my matrix A to the collection of all its eigenvalues. So going essentially from p squared space to the p space, namely the vector of its eigenvalues, this is Lipschitz. Okay, so this looks good. So this seems to say that I can use my Gaussian concentration for the eigenvalues. Okay. Is this true, or is there a kind of problem? I mean, Gaussian concentration would say if the entries of this guy are now Gaussian, are now my independent Gaussians, then the eigenvalues have concentration. But what do I consider as for A? I mean, the entries of A themselves are not my independent Gaussians. But what is A? I mean, A in my setting is this Wishart matrix, which is x times x transpose, and the entries of x are independent Gaussians. So I still have to see whether I can check this intermediate step, whether I can control this. Okay, so what we are interested in, of course, is the mapping which maps x to the eigenvalues of the corresponding Wishart matrix. Okay, so, but we are interested in the mapping where x goes to the eigenvalues of the Wishart matrix, and the Wishart matrix is 1 over n x transpose. So the first eigenvalue of this up to the last eigenvalue of this 1 over n x transpose. Yeah, okay, and so this means, I mean, going from here, going from this matrix to the eigenvalues is Lipschitz, but the first step we have to do is to go from x to x transpose. Or another way is to see, we have really to see that we have the Lipschitz condition for this guy. And of course, this also has an effect on the Lipschitz constant. I mean, here the Lipschitz constant was 1. Okay, but now if we do this, one has to control this. So what I really have to see is what is lambda I of the Wishart matrix 1 over n x transpose compared to the same, to the eigenvalue of a corresponding other matrix of this form. Lambda I of 1 over n y transpose. I mean, that's is what I should control in terms of the difference of the entries in x and y, or in the Frobenius norm of x and y. Okay, so essentially I have here an intermediate quadratic thing which I have to estimate, and I mean, of course, we do this in the usual step. I mean, if I have control on linear terms, how do I get control on quadratic differences? By just like for differentiation, going to quadratic in 2 steps of doing twice. I mean, here I have to replace x by y and x transpose by y transpose. So I should replace things twice. But I'm doing this in steps of replacing only one of them in one step and then doing it again. Okay, so maybe let me write it down. This is the usual thing. So I say this, I can estimate this by this here. I know how to estimate it in terms of the operator norm. I could go directly to the Frobenius norm, but this would not be so good because then I don't really know how to control products. So I estimate this against here, this first step. This is just the difference in the operator norm between x transpose, this guy here, and this guy here, y transpose. So and each of them has a factor 1 over n, which of course I can take out of the norm. Okay, and now I make this transition from x squared to y squared by just replacing the first x by y and then the second x by y. So I'm just writing this here as 1 over n, and then I have here x transpose But in the first step, I compare this, where I replace only the second x by a y. So I compare this with x, y transpose. Okay, and then I'm adding this again. So I haven't really made anything. But in the second step now, I replace this x by a y. So I compare this now with y, y transpose. So that's a usual thing. As you also proved the product rule for differentiation. Okay, so I want the difference between this and this, but I smuggle in this term with a minus and a plus, so I haven't done anything. But now I can estimate this, and in those terms I only have a linear difference. So this is by the triangle inequality, of course, less than this difference, x transpose minus x, y transpose plus x, y transpose minus y, y transpose. And now, of course, here I have the common term x, which I can take out. So I have here x times x transpose minus y transpose. Let me write it. It's 1 over n. So in the first term, I can take out the operator norm of x, and I'm left with x transpose minus y transpose, because for the operator norm, the norm of a product of matrices is less than the product of the norms of them. So that's what I'm using here for the norm. And for the second term, I can take out the y transpose. And so I have here the norm of x minus y times the norm of y transpose. Okay, and now, what we want to do is to estimate the difference in the eigenvalues against the Frobenius norm of the involved matrices. And of course, here I have the difference, and I can estimate this against the Frobenius norm. So this is less than x minus y Frobenius norm. And of course, the one of the transpose is the same as without the transpose. Because I'm summing over the square of all entries. And whether I first transpose my matrix or not, that doesn't make a difference. And of course, this is, I can also estimate as against x minus y Frobenius. Okay, so that's good. But now you see I also have an additional factor here, which I have also to take into account. So this means the Lipschitz constant, which I'm getting for this estimate, is of course this 1 over n, which comes from the rescaling. Then, okay, I have a factor 2 because I have here two terms, but then I also have the operator norm of x and y, which of course is not so clear. That was actually a thing which we talked before. The operator norm, okay, we have now some idea which is good enough for controlling it. So it's good to know something about the operator norm. But let me write it down. So this here, so what we see from here is that the Lipschitz constant is bounded by, so let's say L, my Lipschitz constant is 1 over n. Then I have twice this term, and in each of this term I have either the norm of x or the norm of y. So I should take the maximum of them. So I have here the maximum of the norm of x and the norm of y. Good, okay. And now, of course, if x are now our random matrices, okay, these norms, we should also control them. They should be bounded by something. So how can we control them? And of course, maybe the first idea is, why not? In all our arguments, in the end, we went down to the Frobenius norm, to the Euclidean norm. Why not just doing it here? Because that's something which we can control very easily. But that's something which we should not do here, because the Frobenius norm is really much worse than the operator norm. And if we would replace it here, this would not be good. But let us have a look at this. Because, it also tells us a bit, it depends in which regime we are really working. Because we have here, essentially, we have two dimensions, n and p. P is the size of the data, and n is the size of the observations. How many data do we have? And they should be very large, but the question is, in which way are they going to infinity, let's say. And in one way, I mean, the Frobenius norm for this would be good, but in the other way, and that's the one in which you're interested, it's not good. But maybe we should check this, because this also maybe gives us an idea by comparing the classical regime with the modern regime in which we are interested for our statistics. Okay, so what I'm saying is that it's not good. I mean, the first thing maybe one should try, and of course we should try it and see whether it's good or not. What I'm saying, it's for our cases, it's not good to estimate this. Not good to estimate. Of course, the estimate is okay, but it's not so helpful if I estimate the norm of x against the Frobenius norm of f, and the Frobenius norm of f is the norm when I consider my matrix as a vector. So I mean, I have here, so what do I have here? So x, yeah, x is a n times p matrix. So this would be here the norm of x as a vector in R to the p times n. Okay, yeah. And so, what do we know? I mean, now we would have here an p times n dimensional Gaussian vector, where the entries are normal, independent normal Gaussians. And what do we know about the norm of this? So where does this concentrate? Of course, we can only do concentration, because I mean, the norm of x can be arbitrarily large, because all possibilities are there, but we know it concentrates. And for the norm of a vector, for a Gaussian vector, so where does it concentrate? Yeah, square root of the dimension, and the dimension is here p times n. So I mean, so we know. I mean, that was from the easy concentration phenomena for linear functions. So we know that the Frobenius norm, or the norm as a vector in R to the p times n, concentrates about the square root of the dimension, and the dimension is here p times n. So it's really, I mean, I have a matrix which goes between p and n, so it should be more a p-dimensional object, but here it is really considered as a p times n-dimensional object, as a vector. And I mean, this is not appropriate, or I mean, this says it concentrates here, and this is, yeah, I mean, this can be good or cannot be good, because now we have to specify in what are we really interested. So we have p and n, and in classical statistics, usually you say, I mean, p is a dimension. P is the dimension of my data, the features in which I'm interested, and n is a number of observations. P is fixed, and n I can make as large as I want. I make many observations, and then usually my estimators really converge to what they are. So this would mean P is a fixed quantity, maybe large, but fixed, and then n is going to infinity. That would be the classical statistical regime. And for this, I mean, this estimate here would be good enough. But so let us first look at this. So if P is fixed and n goes to infinity, and I would say this is the classical regime of statistics, classical regime, when you make observations and you want to infer something from those, you have fixed size for the data features, but you can make as many observations as you like. Okay, so n goes to infinity, then actually this estimate would be okay. So why? Yeah, because what is then L? I mean, our Lipschitz constant, what would this be? So this would then be, let's say, yeah, so what would it be? L is here 1 over n 2 times, okay, I have this 2, I have this 1 over n, and I have the maximum of these quantities, but this, okay, I mean, for x and y it's the same for my Gaussian vectors, so this is around the square root of p times n. So I have here the square root of p times n. Okay, but so this is like, yeah, 2. And then the square root of p, I mean, p is now just a fixed number. So this doesn't go to infinity. So I have the square root of p. And then I have here the square root of n. But here I divide by n. So essentially, this goes like 1 over the square root of n. And if n is going to infinity, this goes to 0. And so, I mean, I can really control this. So this is bounded by something. So this behaves like a constant times 1 over the square root of n. And if n goes to infinity, this is very good, because then, I mean, even my Lipschitz, yeah, I mean, I have a Lipschitz constant which goes like this. And if I then take a concentration, then of course in a concentration I get 1 over L squared. So I get e to the minus alpha squared times n. So the n shows up in my concentration estimate. So I mean, the L should go to 0 with the dimension, because the L shows up in my concentration inequality. And then, I mean, in concentration I had e to the minus alpha squared divided by the Lipschitz constant, maybe with another 2 or something here. So you see, if L is like this, then I get here e to the minus alpha squared times n. So this means I have a concentration which goes to 0 if n goes to infinity for some deviations from this value. Okay, so this would be good. Yeah, but that's unfortunately, or maybe fortunately, because otherwise we wouldn't talk about such things. This is not the regime if we are interested, because in our modern times, usually you have P is very big, so maybe you have many features in which you're interested, and the number of observations is also very big, but it's usually of the same order. Usually you make n is comparable to P. And it's much more appropriate to look for the regime where n goes to infinity, but p goes also to infinity with the same speed. So they are proportional, let's say. That's the one in which we are interested, and which is much more appropriate for describing, I mean, statistics of high-dimensional data. Okay, so this would be good if we are interested in this, but we are not interested in this. But now we are interested in, let's say, modern regime of modern data analysis. And there we have the phenomena that P and N are of the same size. I mean, and so, of course, they are very large, so we can try to capture their features if we go asymptotically to infinity. But they should not be independent, but they should go to infinity with the same speed, and say that P is a multiple of N, where gamma is fixed. So for gamma fixed. So the ratio of P by N, this is gamma, this is fixed. So let's say P is 1/2 of N, or 1/3 of 5 times N. Okay, but then what is then? What do we get then from this estimate? Then L would be of the order 2. I have the 1 over N. Okay, and then I have in the square root, I have P times N, but P is now gamma N, and I have another N. So I have the square root of this, and now you see, I mean, I have the square root of N squared. This is N divided by N, and this is constant. So this is essentially a constant, and this doesn't give me good concentration. So I mean, I wouldn't see the dimension here. Things would not go to 0, would not concentrate if the dimension goes to infinity. Okay, so this here behaves like a constant, and this means we don't have no good concentration. I mean, of course, we can still write down our estimates, the probability for something bigger than this, but the estimates we get there don't show concentration with the dimension. I mean, I always say concentration inequality, but of course the inequalities are estimates for the probability that the deviation is bigger than alpha. And then on the other side, of course, in the right scaling, the dimension should show up, so that the other side really goes to 0, usually in an exponential way, if the dimension goes up. The estimates themselves, yeah, I mean, okay, they don't show the dimension explicitly. It depends on the value of this Lipschitz constant, where you have to choose things in the right way. Yeah? And here you see, yeah, your Lipschitz constant doesn't show the right behavior with the dimension. Good. Okay, so this means in this regime in which we are interested, estimating this against the Frobenius norm, so this means looking on our matrices as vectors is not a good idea, because our concentration for the vectors is not good enough. Okay, and I mean usually, yeah, this inequality here, you are very far away from this, so you should only do this in, okay, not, yeah, better stay with the operator norm, and that's what we should have here. But actually we know, I mean, in the beginning I showed you that we have some information about the operator norm, and so now we should use this. I mean, we don't know exactly what the mean is, but we have an idea of the order. So we continue here with the operator norm, because the Frobenius norm does not give us anything interesting. So the operator norm for x. Okay, and for this we have seen that we have a concentration around the square root of p plus the square root of n. That was what I showed you at the beginning. So there we had concentration inequalities. So for this we have concentration around, let's say, constant, and then we had the square root of n plus the square root of p. Okay, and now if p goes with the same speed as n, then this is concentration about the square root of n. And that's again good enough. Then we are really somehow back as in above case. And so we know that with high probability, the L, we can bound it, or we know that it concentrates. So thus, with high probability, the L is of the order, yeah, it's 2 times 1 over n. That's the general terms there. And then the norm, I can estimate it, or it concentrates about C. And then I have the square root of n. And for P, I have gamma times n. So I get something like 1 plus square root of gamma times the square root of n. And you see now again I have the square root of n divided by n, which goes like 1 over the square root of n. So this means again in my concentration inequality, in my estimate for deviations, I get as before the factor n there, which means I get good concentration. So this means this gives, by theorem 3.2, which was our Gaussian concentration for Lipschitz functions, so this gives then in the end a concentration of the eigenvalue of my Wishart matrix around its expected value with probability 2 times exponential, maybe let me write it again, and so it was minus alpha squared divided by 2L squared, and this is of the order exponential of minus, and the L squared is like 1 over square root of n, so I get here really an alpha squared, an n times alpha squared divided by 2, and here I get some, okay, I have here some constant here. I mean, the constants don't matter for those things. Okay. Okay, so we get this as a bound for the probability of deviations by alpha from the mean. As a bound for the probability of deviations alpha from the mean. Good. Okay, and so I mean the conclusion of all this is that if we are in a regime where P is proportional to n and we are going to infinity, the eigenvalue distribution of our Wishart matrix concentrates on its average eigenvalue distribution. So I mean each eigenvalue is very close to its averaged version. Okay, yeah, and so we see we have concentration. I mean, so this means if I do one histogram for one specific choice for this, I will more or less see always the same because it concentrates about the mean. So this means they are very close together. Okay, but again, we have the situation, we have concentration, which is a very strong statement. So we know that I mean, more or less every realization is very close to each other and also very close then to the averaged version, but we don't know what the average version is. So I mean, that's still what we have to do. In the case of the largest eigenvalue, I did not really give you very precise what the average is. Okay, but now for the distribution of all of them, I want to give you what this is, and this is the famous Marchenko-Pastur law, and the distribution, the asymptotic distribution, is the Marchenko-Pastur distribution. So that's what we want to talk about in the following. And I want to give you also main ideas for the proof of this. Not doing all the details, but show you in principle how this is done. Okay, so we have concentration, which means essentially in order to understand what happens with those Wishart matrices, for the eigenvalues, we have to understand the averaged behavior. But this is still something which we have to do. I mean, the average behavior really, this gives us some curves, some histograms. I mean, the fact that we know we always see the same doesn't tell us what we see. So we still have to calculate what we really see. I mean, this is really abstract arguments are nice, but if you really want to see something concrete, we have to be more concrete. We really have to calculate. Somehow we have to calculate the limit eigenvalue distribution. But it's enough to calculate it for the averaged version. And that's really that's the big thing about these random matrices, that you really have this concentration, and averaging is really enough. Essentially, it's just averaging. And I mean, calculating an averaged version is much easier. Or averaging helps really to do calculations. I mean, if you want to calculate for specific entries of your matrix, if you want to calculate the eigenvalue distribution, I mean, there's no way how to do it. Of course, you can draw histograms, but if you average over everything, then you have much more structure. I mean, so averaging helps, and if you know that averaging is close to the generic situation, then you have randomness, but randomness helps you, because randomness helps you to calculate really what the average is. But the average is more or less always the same. So, okay, so philosophical statements are also nice, but I think we should do some work. We really should calculate things. And I mean, we already have seen in numerical simulations that there seems to exist a limit of the eigenvalue distribution of those Wishart matrices, because you were asked to do simulations for them, and actually in a normalization which we have here, dividing by this 1 over n, it was really that, I mean, that was the right scaling, that if we go with n to infinity, really it stabilizes. Okay, so this 1 over n is exactly the right thing, which gives us a limit if n goes to infinity. Good, okay, yeah, and so what we saw there was essentially, I mean, we looked on the eigenvalues, so I mean, you calculated some histograms, you realized your matrix, and then you saw some eigenvalues, and for this you saw some histogram, you draw something like this. Okay. And if n goes to infinity, or for very large n, I mean you got I mean this histogram was very close to very smooth curve. So essentially what you saw there, and I mean that's what we want to prove and understand, is that if n goes to infinity, but in such a way that p also goes to infinity, but p is proportional to n and gamma is fixed, then this will converge to some kind of density, a limit of this histogram, and this is a density, a probability density, which is actually called Marchenko-Pastur. So this goes to something which looks something like this, a density. So the histograms converge for n to infinity to a density, maybe psi, and maybe let me put an MP here for Marchenko-Pastur. And of course, this depends on gamma. I mean, depending on gamma, you will see different shapes. Okay, and so of course, what is the meaning of this? This means, of course, that this density here tells you about how many eigenvalues you see in a given regime. So I mean, if you're looking here, let's say, from A to B, and you ask how many eigenvalues do you have in this interval, then of course it's the number which this histogram here tells you. So how many are there? And this in a limit is given by the area under this curve from A to B. If here's A, here's B, then I mean this part of the histogram will converge to this. And so I mean the number of eigenvalues, average number of eigenvalues here, will converge to this here. That's the meaning of those pictures. So if you take here the number of eigenvalues in, let's say, interval AB, and then you normalize this by P, because you have altogether you have P eigenvalues. So you want to normalize it so that you have a probability distribution, and then you get here a probability density. So this here converges to the integral from A to B over this density dt, which means it's exactly this area under the curve. Okay, so this means the fraction of the eigenvalues in this interval converges to the fraction of the area under the curve. Yeah, and of course, this curve here should be a probability distribution. So this means, so if I'm asking here for all eigenvalues, so I take an interval where they are all sitting, then of course I should get here the integral over the whole density, and this should be 1. Okay, so note, of course, that the integral over everything of my Marchenko-Pastur distribution is equal to 1. Because I ask about the normalized eigenvalues. Good, okay, and so we saw this in our simulations, and actually, yeah, this is really true, and we can give an explicit formula for the curve which we get there, and that's the Marchenko-Pastur law. So I will write it down now, and then we will try to prove this. So that's one of the basic theorems about random matrices. This was proved by Marchenko and Pastur in 1967. So it's usually called Marchenko-Pastur law, and this is the Marchenko-Pastur distribution. And so what does it say? Okay, I will say it a little bit in informal terms. Yeah, I'm saying the histograms of the eigenvalues converge to the Marchenko-Pastur density. Yeah, but I think this should be clear. The main point here is that we really get a formula for the limit, and we want to really calculate and understand this formula. Okay, so what we have is our Gaussian random matrix P times n. So this should be, let this be our standard Gaussian random matrix of size P times n, where all the entries have the normal distribution, standard normal distribution, variance 1, and all independent. Let me write it down. So where all entries xij of this matrix are just a standard normal distribution, and they are of course independent. And then, yeah, if now P and n go to infinity, but in such a way that the ratio is more or less constant, or at least in the limit goes to a constant, which I call gamma. So if P by n go to gamma, and gamma is a fixed number, and let me fix it in the interval 0 to 1. I mean, in assignments, you saw that you can also go to the regime where gamma is bigger than 1, but then actually you also get atoms at 0. Okay, so here we are in the regime where we don't get atoms, and so maybe the formula is nicer to write down, but it's more or less the same in the other regime. Okay, so if P divided by n goes to a constant gamma, which we assume here to be between 0 and 1, and of course n goes to infinity, then the histogram of the eigenvalues of our Wishart matrix, so the histogram of eigenvalues of our Wishart matrix, which I denote by sigma hat, and which is nothing else than 1 over n x transpose, that this converges. And I mean, I have here this normalization 1 over n. So this means effectively you can also say I have rescaled the entries of my matrix X by 1 over square root of n, so that I have replaced here the normal distribution with variance 1 by the one with variance 1 over n. And this is the right scaling, so that you really have a limit. Of course, I mean, otherwise things would explode. So we have to scale the variance, at least the variance of this guy we have to scale so that it has a limit, and it is clear that you have to scale it like this, but then also everything else has a limit. Okay, so this converges to what the histogram of the eigenvalues of this converges to the so-called Marchenko-Pastur density. Density, okay, which I just call psi mp, but for which I can write down a formula. So psi mp, and of course it depends on gamma, so maybe I should also put a gamma somewhere, but okay, we have gamma fixed here. So the density is given by 1 over 2 pi, and I have here gamma and then t, and then I have the square root of gamma plus minus t times t minus gamma minus the square root of this. So this is a density which lives on a interval, a compact interval, which goes from, I mean, where this square root here makes sense, namely from gamma minus to gamma plus. And of course, those are guys which are determined in terms of gamma. So namely, so gamma minus is just 1 minus square root of gamma squared, and gamma plus the same with a plus here. So gamma plus is 1 plus the square root of gamma squared. Okay, so that's the Marchenko-Pastur law. And yeah, you can, you were asked to compare really this concrete explicit form of a density with the histograms, and this fits really very well. Good, okay, and maybe let me start with a few remarks about the proof. So next time we will do the main steps in the proof, the main calculation. I mean, somehow, I mean, at some point we should see how do I get, I mean, where does this formula come from? I mean, I have to calculate it somehow. I mean, it's absolutely not clear how this comes. So I mean, I want to show you next time how you can get it, but maybe let me first make a few remarks that, I mean, even, how do you prove such a statement? Because it's a statement about the histograms, that they converge to density, and maybe that's not a way we are going to prove it, because, I mean, talking about histograms is maybe not so clear how we should deal with them. So, but maybe we can formulate our statement in the form, note that the statement is of the form. So I mean I'm taking the average of the eigenvalues which are in the interval AB. So what I'm doing is for each eigenvalue I'm looking whether it's in the interval AB or not. So this means to each eigenvalue I apply essentially a characteristic function. So this means I normalize it by 1 over p, and then I'm summing over all my eigenvalues, and for each of them I'm checking whether it is in this interval or not. Okay, where f is now the characteristic function of this interval. So it just means it, I mean this guy is 1 if lambda I is in the interval, and it is 0 if it is not. Okay, and I'm claiming that this converges if n goes to infinity, but such that p also goes to infinity as gamma n, that this converges, yeah, I mean to the area under this psi from a to b, but of course this I can also write as an integral over the characteristic function of the interval ab. So this I can write as the integral over f of t psi mp dt. Where of course here this f is a characteristic function of the interval ab. So I mean this is just a function which is 0 outside of the interval, and it is 1 inside. So it's just a function which checks whether my argument is in this interval or not. Okay, yeah, and of course I mean lambda 1 up to lambda p are here the eigenvalues of my Wishart matrix. Good. Okay, and so I mean yeah, proving this in this form is not really so clear, and so how the proof proceeds is usually that you replace these characteristic functions by other functions and you prove the same kind of convergence. Okay, and then things are much better. Okay, because for other functions you can really prove this quite nicely. Okay, so proving this here, let me call it star, this equation. So proving star directly is not clear. But actually one knows by general machinery theory that it's enough to prove such a statement for other classes of functions. I mean here you have to prove it not just for one a and b, but for all a and b. So for all characteristic functions you have to prove a statement like this. That's more or less what we are saying, that the histograms converge. Okay, but knowing it for all characteristic functions is the same as knowing it for other classes of functions, and there are typically two classes of functions which one can consider. So namely, yeah, so let me first, so proving it is not so clear, but it can be achieved by looking on other classes of functions. So what can be achieved for other classes of functions. So okay, so I'm saying instead of proving this for the characteristic functions, so instead of proving star for, I mean that's what we really claim in our theorem, and maybe what we would like to prove, that this statement is true for all f which are characteristic functions for some interval. So for all intervals, yeah, that instead of proving this, one can also prove it. One proves it for other classes of functions, and there are two possibilities which give two different ways of proving this theorem. So namely, one is that I just take powers. So I take f of t just as t to the n for some power n, and I have to do this for all. So I consider all f of t is gleich t to the n for all natural powers. And I mean then what I'm doing is more or less looking on the moments of my guys. So So I mean here then I have t to the n integrated with respect to the density. Those are the moments of my Marchenko-Pastur distribution, and I have to see accordingly that, in a sense, the moments of the eigenvalues also go to this. And I mean, proving this usually is so this is looking on a moment, and this is the moment method, which tries to understand the moments of this. So these are the moments. But maybe another possibility. I mean, moments usually is a combinatorial thing. There's a lot of combinatorics involved to understand the moments and what they are in the limit, and whether one can count them or not. And another more analytic way is to look on functions of the form f of t is equal to 1 over t minus z, where z is a complex number. So for each complex number z, I'm looking on this. Those guys are usually called resolvents. So I'm looking on the resolvent, and this is the resolvent method. So then I have to do this for all z. And actually, I mean, I go to the complex numbers because if I'm looking on this function and t is in the domain over which I integrate, I mean, if this guy would be in a domain over which I integrate, then I would have here 1 over 0, and I might have problems. So it's better with the set. I should stay away from the support of my measure. And I mean here the measure is just on a real axis. So if I go in the complex plane, I don't have problems. Then this thing here is always invertible. So this means I'm looking on this for all, let's say C in the upper half plane, or maybe the lower half plane. But in any case, I should avoid maybe the real axis. But if I know this for complex numbers outside the real axis, this corresponding statement, that's good enough. Okay, and so I mean this here is called the resolvent. So that's the resolvent method. Okay, and so I mean one knows by general measure theoretic tools and statements that in our situation proving 1 for all characteristic functions is equivalent to proving either 2 for all moments or either 3 for all resolvents. So what we will do is, usually I like combinatorics, so usually I do moments, but okay, I also like analysis. So actually we do 3. So I want to show you how we can prove, and in particular how by understanding essentially the limit of these functions here, by getting something for the limit, how this gives us the Marchenko-Pastur distribution. Also I get it concretely out of this. So it's, so there should be, we should do some calculations. We should calculate the limits, what they are, and if we know what the limit for those functions are, then this should tell us that we have the Marchenko-Pastur distribution. And that's what I want to show you next time, how this can be done. Okay, but maybe the last remark is, of course, we prove here that this here happens in generic situations, so the probability that this goes to this is very large, and by concentration we know this. We know that those functions concentrate, and also those functions concentrate. So by concentration we know that actually individual realizations have a very high probability to be close to the average. So this means what we have to prove is this here only in the averaged version. So this means we average here over all possibilities, and then we have to show that it converges to this. And this guy is deterministic. I mean, this is really one limit. So we really have one limit object to which we converge, and this is more or less also the averaged version of this. But here we can take the average, and this makes of course the arguments really simple. I mean, no, not simple, but it allows us to do the arguments that we really can calculate this here. Okay, so it's good to know that we have concentration, so that instead of proving this for all resolvents, that this happens with high probability for most of them, it's enough to show that the average version of this converges, because by general arguments we already know that we have concentration. Good. Okay, but I think I will stop here, and next time we then really will We'll give you the main ideas of the proof. Maybe not all all the technical details, but the main ideas, so that I think we really see how we get, or from where we get this explicit formula for Marchenko-Pastur. Good, that's it for today.